So by expressing as well q of r, so we express q of r as this is parenthesis the integral over the 3r prime delta 3 of r minus r prime of q of r prime. Okay, so then in q of r prime, it comes out to be the following. So then, sorry, q of r comes out to be, if I replace this delta 3 of r minus r prime from this equation that is satisfied by the Schrödinger equation, so q of r is equal to this integral over the 3r prime Helmholtz equation Laplacian plus k square d of r minus r prime times q of r prime. So then this is basically what we have as the source in terms of the Green's function. Okay, so now we're just going to consider this equation here to actually derive the Green's function from this equation. So then this is how it's going to look like. So then, so we start, let's change color, let's go for light blue. So then the Helmholtz equation, g of r equals to the delta 3r. Okay, so then what we're going to do is that we're going to multiply both sides by e to the I k r, and then we're going to integrate. Okay, so then this will give us let me move this here because it's kind of uncomfortable. So then Laplacian plus kappa square g of r e to the I q dot r is equal to delta 3 of r times e to the I q dot r. Now what we're going to do is that we're going to integrate both sides with respect to the 3r. And then this is going to give us a 1 here. And then we will have an equation which is delta square or nabla plus kappa square g of r e to the I q dot r the 3r equal 1. This is our new equation, and from this equation we might start getting ready to solve the Green's function. So then now if we integrate, we have to integrate something here like this. So this is not so complicated, but you have to do it by yourself. I have done it in other videos. So then what we can do is just, we have the integral k square, g of r here, e to the I q dot r, the 3r, plus the integral of this Laplacian times g of r, e to the I q dot r, the 3r. And what we have to do here is this. So then you just note here that this thing here is just the Fourier transform times k squared, the Fourier transform of g. So this is g of q. Okay, and then this is not exactly the Fourier transform, but if you actually use integration by parts and exchange this Laplacian, and instead of having the Laplacian on g, Then you have the Laplacian on the e to the iq dot r. So then you will end up with something like minus the absolute value of q square times g of q. Okay, so then and that's what you're going to end up with. This will be equal to 1, so that means that g of q, the Green's function in the reciprocal domain, is going to be equal to 1 divided by k square minus q square. Okay, this is what the Green's function is going to look like in the reciprocal domain. And now we have to invert this Green's function. I mean, we have to go to the real domain, and this is the big pain. So then, but if you are in my channel, I guess all of you guys are already used to some algebra, so it's not going to be a big deal. Let's do it in orange. So then now, so you can express this in the pole form as well. So you can say that this GQ is equal to 1 divided by k square minus q square, and this is just the product of this pole form, which is k plus q times 1 divided by k minus q. This is another form of expressing this if you like. And then I think this color is not a good idea because we cannot see it so good. Let's go to green. And then the Green's function in the coordinate basis is equal to the integral over d3q divided by 2 pi cube g of q e to the minus I q dot r. So this is the integral we have to solve. So there was going to be some complex calculus around, not so complex, I hope. So then this is equal to the integral over d3q divided by 2 pi cube. This is e to the minus I k dot r divided by k square minus q square. Okay, so then and now, what we're going to do is that we're going to split this integral in spherical coordinates, and then we're going to do the following. We're going to say that theta is the angle between q and r. Okay, so then let's write it in spherical coordinates. So then we have 1 over 2 pi cube. Here we have an integral from 0 to 2 pi of d phi. So this integral also goes with 1 to pi here. Okay, so then we have here the integral from 0 to plus infinity of q square dq divided by k square minus q square. That's alright. And then from 0 to pi e to the minus I q dot r sine theta d theta. Remember what I just said. This angle theta in spherical coordinates is the angle bearing r and q. Okay, that's that angle. So knowing that, we can proceed to write it in this way. So then this is equal to just 1 divided by 2 pi square. So the integral from 0 to plus infinity of q square dq divided by k square minus q square, and the integral from 0 to pi of e to the minus I QR cos theta, which is the dot product between these two, times the, like this. So sine of theta, it comes out to be the derivative. It comes out to be the derivative of minus cosine theta. So then, so minus the derivative of minus cosine theta with respect to theta, the theta. Okay? So that means that we can replace, we do the following replacement. So then we can say that u is equal to cosine theta. Okay? This we can say. And we can say that du is equal to minus sine theta d theta. Okay, so we can replace just this here, and now we can say that when theta is pi, so that means that u of pi is equal to cosine of pi, which is equal to minus 1, and u of 0 is equal to cosine of 0, which is equal to 1. So that means that this minus sign is washed out by interchanging the limits, because these limits will go from 1 to minus 1. And if I just put the limits instead of minus 1 to minus 1, minus 1 to 1, so I flip the sign and then I wash out this minus sign that I have here. And then g of r can be written as 1 over 2 pi square integral from minus infinity to plus infinity of q squared dq, k squared minus q squared, integral from minus 1 to 1 of e to the minus I qr u du. Well, this is some expression. It's not too bad. So then, but we have to do something with this expression, of course. And then this expression, if we calculate the integral for this expression, so then it's going to come out to look something like this. So we have to keep on reducing the expression. Let's see how this is going to look like. This is going to be a mess in a little bit, but sorry, this is not minus infinity. What I put here, this is 0. My big apologies for that gross mistake. So then this is 0 to plus infinity, q squared dq, q squared minus k squared minus q squared, and then this integral here is going to be this exponential evaluated at u equal to 1. So this is going to be e to the minus I qr minus e to the I qr. That sounds right, divided by minus I qr. This looks like a sine, and it does look like a sine, but for integration reasons, we're not going to express that as a sine, because we're going to use the residual theorem to evaluate, because this is going to have to be evaluated in a evaluated in a complex plane, so in a trajectory. Okay, so then it's better to keep this e to the I something. So now what we're going to choose to do is that we're going to cancel this q. We're going to cancel it with this q. Okay, we're going to put this I upstairs, and we're going to move this r outside, so then this is going to look like this. It's going to look like I divided by 4 pi square r. Now we have moved everything here outside, and there we're just going to keep the integral around some trajectory in the complex plane from 0 to plus infinity of q e. Now the minus sign that we have here, it was flipped because I put the I upstairs. Okay, so, and then to keep this as a plus, so I'm going to write like this. I'm going to write here first, just a minute, doesn't look too static. I'm going to write here e to the I q r minus e to the minus I q r, but then instead downstairs I'm going to write q squared minus k squared. Okay, and then this is the integral that I'm left with to actually evaluate respect to q. So then, and if I evaluate this integral, I will be all done with the Green's function. So then, at least in the real domain. So then what we're going to do here is that we're going to apply some strategic stuff. So let me see how to put this into words. So then, yeah, we are going to, we need for this integration in the complex plane, let me explain what I'm trying to achieve. So for this integration in the complex plane, we need to integrate usually in the complex plane, as I explained in the chapter for Green's functions in classical physics. We have two semicircles over which we want to integrate, and then this has been, of course, the omega plane, but this is now the q plane, so then it doesn't make such huge difference, but it's just to explain. So then, but then what we're going to do is that we need to integrate, we need to take this semicircle, the length of this semicircle, or the diameter of the semicircle, we want to take it to minus infinity. This is what we want to do. So then, so that means that this integral, somehow, this integral should be evaluated from minus infinity to plus infinity over some semicircle. This is what I'm trying to do now. So then, and how am I going to do this? So then I'm going to do this, I think, in the following way. So then let me try the following thing, otherwise we're going to try something else. So then we're going to split this integral into two integrals. Okay? So then, and we're going to do it in the following way, and I think we should really change color now, because this is kind of a different step. So we're going to say that this is 1/2 times I divided by 4 pi square r integral from 0 to plus infinity. We should erase this integral like that. This is just some normal integral now. So then this is of q e to the I q r minus e to the minus I q r dq q square minus k square. Okay, now the second integral is going to be the same because we just split the integral in half. Integral is like this, like integral is equal to 1/2 integral plus 1/2 integral. This is what I just did. So then now this is plus 1/2 times I divided by 4 pi square r, integral from 0 to plus infinity, q e to the iqr minus e to the minus iqr dq divided by q squared minus k squared. Now, here's the trick. So the trick here is that if we change q to minus q in this integral, nothing is going to happen. And when I mean nothing is going to happen, I mean nothing. Okay? So then it's going to remain the exact same integral. So if I change q to minus q, this guy here is going to be this guy here is going to be e to the iq. This guy here is going to be e to the minus iq. This guy is going to be minus q. This is going to be d of minus q. Minus is minus, goes away. So then we will just pick up a minus sign, and then this minus sign can be reverted by changing the integration limits. And since q goes to minus q, so infinity goes to minus infinity, so then this actually, when I go here q to minus q, the limits of this integral will change from 0 to infinity to 0 to minus infinity. Okay, this is what will happen. And if that's what actually will happen, so then this integral is going to be end up written as I divided by 8 pi square r, integral from minus infinity to plus infinity, q e to the iqr minus e to the minus iqr dq divided by q squared minus k squared. Okay, this is the trick that we want to perform. And now we want to actually calculate this, or we want to actually evaluate this using Cauchy's theorem for complex integrals. Okay, so then for that we have to write this in the pole form. So then we write I divided by a pi square r, integral over some circle. That's going to be two semicircles of q e to the iqr minus e to the minus iqr dq divided by q plus k and q minus k. We have two poles and we will have two semicircles, so we have to choose which pole goes on what semicircle to actually integrate this. So then we have two semicircles, and then we're going to do this. We're going to plot the poles here. So this pole here is, this one is q equal to k, and this one is q equal to minus k. So for these two semicircles, we're going to deform the semicircle a little bit. The upper one, we're going to deform it in such a way that the upper semicircle is not going to contain q equals to minus k. Okay, it's not going to contain that one, but it will contain q equals to k. This is what the first semicircle called C plus is going to look like. So it's going to contain only one pole. Okay, and the second semicircle is going to contain this one is going to contain the pole q equals to minus k, but it's not going to contain q equals to k. And this is going to be semicircle C minus. Okay, so then, and because of the orientation of the integrals, so then this one goes on the clockwise, and the upper one goes anti-clockwise, which is this direction is positive. So then we're going to write the integral as two separate integrals in two different semicircles. And we're going to evaluate this. We're going to evaluate, let me see here. So then, yeah. So then we're going to split this integral, these two guys. We will split these two integrals. So then we will write it. Let's write it again. So the integral is going to look like this. Now that we have already defined the semicircles over which we're going to integrate. So that's good. So then 8 pi square r integral of from minus infinity to plus infinity of q e to the I qr divided by q plus k times q minus k, and this is minus I, this is of course the q, this is minus I divided by a pi square r integral from minus infinity to plus infinity of q e to the minus I qr dq divided by q plus k q minus k. So then, and we're going to choose that the first one, we're going to evaluate the first one over C plus, and the second one over C minus. Okay. And then in a different video, I will explain why I choose these contours the way I choose them. Okay. So then now, if I apply Cauchy's theorem to this, so then Cauchy's theorem tells me that I should multiply the integral f of z dz is equal to 2 pi I times the sum of the residues of f. Okay, so then, and this is exactly what I'm going to do. And then since there's only one pole at each side, so then I'm going to do it like this. So then I'm going to take I 8 pi square r times 2 pi I from Cauchy's theorem times q minus k, which is one of the poles. So then q minus k, which is the pole, everything evaluated at one pole. So then, and since there's only one pole, so I just use this q minus k, but I don't use q plus k because they contour that the first contour does not contain q equals to minus k as a pole, so it only contains q equals to k as a pole. So this is one of the tricks. Okay, so then, and this is times q times e to the I qr divided by q plus k q minus k, everything evaluated at q equals to k. Okay, so this is the first term, and the second term with the minus sign is minus I divided by 2 by 8 pi square r. Now this is time minus 2 pi I. And why is minus 2 pi I and I 2 pi I? Because the orientation of the contour C minus, which is the one that I have chosen to integrate over the second integral, goes in an opposite direction compared to the direction of the contour C plus. That's why this is minus 2 pi I and the other one is 2 pi I. So then this is very clear. We take anti-clockwise as positive direction, and that's arbitrary. You can take whichever you like as positive direction as long as you keep the convention all the way through. So then this is now k plus q plus k times q times e to the minus I qr divided by q plus k, q minus k, everything evaluated at q equals minus k, because it's the actual pole that C minus is embracing. It's embracing q equals 2 minus k. Okay, so then once we have this thing here, let's cancel stuff. This goes with this. Okay, if I evaluate this at q equals to k, so then this is k here. Okay, this is 2k. So then we write like this. We write I divided by 8 r square, 8 pi square r 2 pi I times k here divided by 2k here times e to the I kr. Okay, and the second term is minus, this term will be minus here, minus I divided by 8 pi square r times minus 2 pi I. This cancels with this, so then we get here k, we get here e to the plus, oh, this is minus k here because we're evaluating the q's in minus k, and this is plus I kr divided by minus 2k. Okay, so then here we can start canceling stuff. 2 pi I and 1 pi here, and this goes away. This I and I, it's a minus sign. This k and k goes away. The same thing here. This I and I is a minus sign. This 2 and this 2. This pi with this pi. So then we end up with upstairs minus I divided by 4 pi r e minus I, no, because the minus I went away, sorry. So this is just the 1. This is just the 1 here, e to the I kappa r. Okay, this is let me see, oh no, because this is 1/8 here, this is still 1/8, and this is minus 1 divided by 8 pi r e to the I kr. Okay, that means that the Green's function g of r is equal to 1 over 4 pi r e to the I k r. And then we have derived the result on the Green's function from the Schrödinger equation for an arbitrary potential, and then we will see now how this will look like when we actually try to solve the Schrödinger equation with this Green's function. I hope you enjoy the derivation as much as I do enjoy the derivations. Sometimes they're a little bit lengthy, but this is just how it is. So thank you very much.